Lesson 21. Complex products, powers, quotients, and roots. In this lesson, we will discuss more about the complex polar representation of complex numbers, as well as the reason of why we have that representation and why we would want to use that over the more familiar rectangular form of a complex number. We have here that suppose z and w are complex numbers with polar forms z equals modulus of z, CIS of alpha, and w is the modulus of w, CIS of beta. We have a few rules that will cover how to take the product or multiplication of the two complex numbers, the quotient or division of the two complex numbers, and then also how to take the power or a complex number to any particular power, which is going to be the main concern in this lesson. Now the product rule here, we have the modulus of z times the modulus of w times CIS of alpha plus beta. Where this is coming from is what would happen if you were to take the two complex numbers mod z CIS of alpha times mod w CIS of beta. If I do that real quick, what that would look like is the modulus of z, and I'll expand what CIS means as cosine of alpha plus I times sine of alpha. And we're multiplying that by mod w times cosine of beta plus I times sine of beta. Well, here, because we have the two moduluses in this overall multiplication, I can move those to the front to separate them, and then I can distribute with the two binomial terms that I have here. If I do that, I will have modulus of z times modulus of w, so we see where that beginning part is coming from. And then if I distribute this using the FOIL method, I first will have cosine times cosine. So cosine alpha, cosine of beta. I will then also take cosine of alpha multiplied by I sine of beta. So plus I times cosine alpha sine of beta. If I continue with the FOIL method, I will then multiply the two inside terms of I sine of alpha and cosine of beta. So plus I sine of alpha, cosine of beta. And lastly, I times sine of alpha times I times sine of beta. Note that that would give me I squared, otherwise known as minus 1. So minus 1 sine of alpha, sine of beta. And I'll just keep that as just a minus then. There are a couple terms here that still have the complex or the imaginary part of square root of negative 1, or I, represented there. So let's group those two terms together. I have cosine of alpha, cosine of beta, minus sine of alpha, sine of beta. And with the I terms, I have I times the other two, which would be, if I put this in a reverse order, I'll say sine of alpha, cosine of beta, taking this term, and then adding that to the other term. Cosine of alpha, sine of beta. Now the reason that I grouped these in this manner, and also reordered the last two terms there, is if I look at these pieces, cosine of alpha, cosine of beta, minus sine of alpha, sine of beta, that is the sum identity for cosine. That is cosine of alpha plus beta. Whereas sine of alpha, cosine of beta, plus cosine of alpha, sine of beta, that is the sum identity for sine. So what we really have here is another cosine of an angle measure plus I times sine of an angle measure. That angle measure happens to be the sum of alpha plus beta, and that is where we get the expression of mod z mod w times CIS of alpha plus beta. So that's where that product rule is coming from. And that's a relatively nice way to go about that. The quotient rule would be the same application of this process, except all that would happen here is that the angle measure of beta would be considered negative in this case. So instead of multiplying the two moduluses, you're going to be dividing them. And instead of adding the two angle measures, you're going to be subtracting the first minus the second. That's where the quotient rule comes from. The power rule, on the other hand, is what would happen if I took that product rule and was just taking the product of one number times itself, or z times z. If I did that, if these two moduluses were the same, then I'm multiplying the same number by itself, which means I could take that to an exponent. And if these two angle measures were the same, that means I'm adding them together. So I could do alpha plus alpha, which I could also write as 2 times alpha. And we can expand on that and do the product rule with z times z times z times z. So we can multiply z many, many times. And all we're going to see is that the exponent on the modulus is going to increase, and the coefficient on your angle measure is going to increase. It'll all just depend on what power you're doing. And that's where our power rule is going to come from. We have the power rule is the modulus of z taken to that power of n times CIS of n times your angle measure alpha. This is one of the best things to use this complex polar representation for. With the product and quotient rule, you can relatively easily do that in rectangular form as well. However, with the power rule, this would allow us to take a complex number to a really, really high power. And we can do that in a pretty short amount of time when it's in complex polar form. Whereas if you're taking a binomial a plus bi rectangular form of a complex number, like 2 plus 3i to the 7th power, that would be a little timely to do, because you would be multiplying 2 plus 3i times 2 plus 3i times 2 plus 3i and distributing all those values accordingly. It is far faster to do this in complex polar form, and if you need in rectangular, then to convert back. The power rule for complex numbers here in polar form, we do call it the power rule, but it is sometimes also known as De Moivre's theorem. So it has multiple different names.